Something about the signal did not feel random. It was faint, buried under layers of static, almost invisible unless you were looking for it. But once it was seen, it could not be unseen. A thin line of order inside what should have been pure cosmic chaos. The data had been flowing for weeks, quiet and ordinary, and then suddenly, hidden inside that stream of noise, there it was. Not loud, not dramatic, just steady, calm, repeating dot. At first, no one said anything publicly. The numbers were small. The pattern was subtle. Space is full of strange readings. Instruments glitch, signals bounce, background radiation rises and falls like waves in a restless ocean. Most anomalies fade after closer inspection. That is how science works. You observe, you question, and usually you find a simple answer, but this one did not fade. The strange part was not the strength of the signal, it was its rhythm. Natural cosmic noise is messy. It spreads across frequencies in unpredictable ways. It rises and falls without care. But inside the noise surrounding 3I Atlas, researchers noticed a narrow band of repeating pulses. They were not evenly spaced like a clock. They were not strong enough to scream in tension. Yet they held a structure that felt deliberate. To understand why this matters, we need to think about what noise really means. When radio telescopes listen to space, they hear a storm of energy. Stars flare, pulsars spin, galaxies emit radiation across the spectrum. Even empty space hums with leftover energy from the early universe. Most of it blends together into a kind of cosmic static. It is like standing in a crowded room where everyone is speaking at once. You do not expect a whisper to stand out, yet that whisper was there. Scientists filtered the data again and again. They removed interference from Earth. They corrected for solar radiation. They checked the alignment of their instruments. The pattern remained. It was weak, but it repeated over several observation cycles. Each time 3I Atlas moved into a clearer position relative to Earth, the narrow pulse returned. The first explanation was simple. Maybe the object's surface was reflecting sunlight in a strange way. Some bodies spin unevenly. As they rotate, they can flash brighter for a brief moment, creating repeating changes in observed energy. That seemed reasonable. Many asteroids behave like that. But the frequency did not match a normal rotation curve. If 3I Atlas were simply spinning, the pulses would follow a predictable rotation period. Instead, the spacing between them shifted slightly, each cycle, as if adjusting, not randomly, but not perfectly steady either. It was as if the signal was compensating for motion. That word made people uncomfortable. Compensating. The research teams avoided dramatic language. They described it as structured modulation. That means the signal changed in a pattern that did not look purely accidental. They were careful. They did not say artificial. They did not say intentional. They simply said unusual. To measure how unusual, they compared it to known cosmic sources. Pulsars, for example, are spinning neutron stars that emit beams of radiation like lighthouse beams. Their signals are extremely regular. Some are so precise, they rival atomic clocks. The pulses from 3I Atlas were nothing like that. They were softer, less precise, but still more ordered than background noise should allow. Then came the deeper analysis. When researchers zoomed in on the waveform, they found slight variations in amplitude. Amplitude is simply the height of the wave, how strong the signal appears. Instead of random spikes, there were clusters, small groups of pulses that seemed to form sequences. Not in any language anyone recognized, but in patterns of 3 and 5.3 pulses, pause, 5 pulses, longer pause, then 3 again. At first, this was dismissed as coincidence. Human brains are good at seeing patterns even when none exist. It is a survival instinct. We look for order because order once meant safety. But the numbers continued to appear. Over several weeks, independent teams ran blind analyses. They removed labels from the data and asked other researchers to search for anomalies without telling them what to expect. The same clusters were identified again. Still, caution ruled the conversation. Space is vast. Probability alone allows for rare arrangements. If you listen long enough, strange coincidences will happen. But there was another layer. The signal's frequency band was unusually narrow. Natural emissions often spread across wide ranges. This one stayed confined, like a beam rather than a floodlight. Narrow band signals are interesting because they require focused energy. They are not impossible in nature, but they are less common. As the months passed, the pulses weakened slightly as distance increased, just as expected, with an object moving farther from Earth. That was normal. What was not normal was the slight drift in frequency that seemed to adjust against Doppler shift. Doppler shift is the change in frequency caused by motion. It is why a passing siren sounds higher as it approaches and lower as it moves away. In space, moving objects also shift their signal frequencies. Scientists calculate that shift precisely based on known velocities. The pulses from 3I Atlas drifted almost exactly as predicted by its trajectory, but with small corrections layered on top. Tiny offsets that seemed to hold the core pattern stable relative to Earth's frame of reference. That detail changed the mood in several observatories, because if a signal naturally emits at one frequency, it should shift smoothly with motion. It should not appear to correct itself. And yet the central pattern remained remarkably aligned. Some suggested gravitational interactions, perhaps unseen debris around the object, was influencing the readings. Others proposed that gas jets from the surface were creating brief bursts of radio emission. Comet-like behavior can be messy and complex. Simulations were run, models were tested, none reproduced the narrowband stability combined with clustered pulse groupings. The theory began to circulate quietly. Not in headlines, not in press releases, but in late-night conversations between senior researchers. What if the signal was not a byproduct of natural processes? What if it was embedded within the noise itself? The beacon theory did not claim that 3I Atlas was a spacecraft. It did not suggest flashing lights or engines. It proposed something more subtle. That the object, whether natural or artificial, carried within it a repeating information pattern hidden inside ordinary cosmic radiation, a signal masked as noise. The idea was unsettling because it required no dramatic structure, no shining metal, no visible technology, just math, just order where chaos should dominate. To test the idea, researchers applied information theory. They measured entropy, which is a way of describing randomness. Pure noise has high entropy. Structured signals have lower entropy because they follow rules. When the pulses were isolated, the entropy dropped slightly below expected cosmic background levels. Not enough to prove design. Enough to raise eyebrows. The most cautious voices reminded everyone of history. There have been false alarms before. Signals once thought mysterious later turned out to be satellites, faulty cables, even microwave ovens in observatories. Extraordinary claims demand extraordinary evidence. And yet no clear terrestrial source could be found. The signal did not match known communication bands. It did not align with Earth-based transmissions. Its direction traced back consistently to the moving path of 3I Atlas. Weeks turned into months. Data accumulated. The pattern did not grow stronger. It did not evolve dramatically. It simply continued, like a quiet heartbeat under layers of static. For an older host like me, who has watched decades of space exploration unfold, the most striking part is not excitement. It is restraint. The silence in the scientific community is louder than any announcement. When experts avoid bold claims, it often means they are thinking carefully. Because the deeper question is not whether the pulses exist, they do. The question is what creates them. Natural explanations still lead the list. Unknown magnetic interactions, complex surface materials, plasma effects that we do not yet fully understand. The universe is full of surprises. But there is a detail that refuses to rest. When the signal is converted into audio range and slowed down, the clustered pulses create a repeating cadence. It is faint, but rhythmic, not music, not speech, just a repeating structure that feels measured. Some researchers compared it to a lighthouse signal hidden inside fog, not meant to shout, but meant to persist. If it were a beacon, it would be a quiet one, not broadcasting loudly across galaxies, but whispering steadily into the dark. A signal designed not for immediate attention, but for eventual discovery. That possibility changes how we look at everything else. Because if a signal can hide inside natural noise, then we may have overlooked many before. We often search for obvious signs of intelligence. Bright flashes, strong pulses, clear modulation. But what if the smarter approach is camouflage? Nature provides the perfect cover. Cosmic radiation is everywhere. Embedding information inside it would require subtle control, not massive energy. A narrow band carrier wave, masked within background levels, repeating slowly over time. No dramatic arrival. No invasion, just presence. There is still no proof of intent. Only questions. The beacon theory remains exactly that, a theory. But it forces us to reconsider assumptions. We assume that intelligence would announce itself boldly. We assume communication would be obvious. What if it is patient instead? As 3I Atlas continues its journey, drifting farther from the inner solar system, the signal grows weaker. Soon it may fade beyond detection, and if it does, we will be left with recordings, models, and debates. The final analysis reports will likely use careful language. Inconclusive, anomalous, requires further study. Science moves slowly for a reason. It protects us from jumping to conclusions. But sometimes, history shows that quiet anomalies become turning points. We once ignored strange pulses from the sky until we realized they were pulsars. We once dismissed cosmic microwave background noise until we understood it was the echo of the Big Bang. Discovery often begins with confusion. And right now, confusion is exactly where we stand. The beacon theory does not demand belief. It invites patience. It asks us to look again at the line between randomness and order. It reminds us that noise is not always meaningless. For those who have followed 3I Atlas from the beginning, this chapter feels different. Not explosive, not cinematic in the usual way, but deeper, more subtle. A quiet tension that lingers. If there is something hidden inside that signal, it is not shouting, it is waiting. And the question that now hangs over observatories around the world is simple, yet profound. Are we listening closely enough? For a while the signal seemed to settle into the background of daily observation. It was still there, still repeating in its quiet way, but the urgency faded. Scientists returned to their normal routines. Telescopes shifted to other targets. New discoveries demanded attention. The universe does not pause for one mystery. But deep in archived datasets, something unexpected appeared. A graduate student, reviewing older recordings to test a new filtering algorithm, noticed that the earliest data from 3I Atlas contained the same narrowband signature even before anyone officially reported it. It was weaker then, almost invisible, but the clustered pulses were present. 3, pause, 5, longer pause, 3 again, . That meant the signal had not suddenly begun. It had been there from the start. When the timeline was mapped carefully, another detail emerged. The strength of the pulses did not rise smoothly as distance changed. There were slight surges at specific points along the object's path. Not random surges, but peaks that aligned with geometric positions relative to Earth and the Sun. Imagine 3 points in space forming a triangle. As 3I Atlas moved, there were moments when that triangle reached a particular alignment. During those windows, the signal clarity improved slightly, as if transmission conditions had optimized. The natural explanation was geometry. Radio signals can be affected by solar wind, magnetic fields, and plasma density. Certain alignments might reduce interference. That was reasonable. But when researchers modeled solar wind density and known magnetic variations during those peaks, the numbers did not fully explain the improvement in signal structure. The pulses became not only clearer, but slightly more stable during those alignments. Stable, that word returned again. By now, several independent observatories had confirmed the pattern. The signal was not tied to a single instrument. It was not a local glitch. It traveled with 3I Atlas, shifting exactly as its position shifted. A quiet working group formed, no public announcements, no dramatic press conferences, just careful minds comparing data across continents. They agreed on one rule: assume nothing. Start with physics. Stay grounded. One physicist proposed a simple but powerful test. If the signal were purely natural, its internal structure should degrade as noise increases. In other words, the pattern should become more chaotic when interference grows stronger. But if some underlying mechanism were maintaining structure, even weakly, then the ratio between signal clusters might remain consistent. They measured that ratio across months of data. Even when overall strength dropped, the relative spacing between the pulse groups stayed within a narrow tolerance range. Not perfect, not machine-like, but tighter than random chance would predict. At this point, conversations began to shift from, is it noise, to what kind of process produces this? Several new hypotheses appeared. One suggested that 3I Atlas might contain unusual crystalline structures, Certain crystals, under stress or temperature changes, can emit radio frequencies in patterned ways. Perhaps the object's internal composition was interacting with solar radiation in a rare configuration. Laboratory simulations attempted to recreate similar emissions. Crystals were heated, cooled, rotated under electromagnetic fields. Some produced faint pulses. None matched the narrow-band stability combined with clustered repetitions seen in the data. Another theory focused on magnetism. If the object possessed a strong internal magnetic field interacting with solar wind, it might generate structured emissions, but measurements of its magnetic signature showed nothing extraordinary. It behaved like a typical interstellar body, at least from what instruments could detect. And then came the twist that changed the emotional tone of the entire discussion. A mathematician, not an astronomer, suggested analyzing the pulse intervals using prime number testing. Prime numbers are numbers that can only be divided by 1 and themselves. They are often discussed in theories about intelligent communication because they represent a universal mathematical concept unlikely to arise randomly in sequence. No one expected much from this test. It felt almost philosophical. But when the intervals between clusters were converted into time units and compared statistically, a subtle pattern emerged. The longer pauses, though not identical, tended to cluster around values close to prime multiples of a base unit measured in milliseconds. It was not clean, it was not exact, but the clustering was strong enough to reduce the probability of pure randomness below earlier estimates. Caution intensified. The working group expanded to include experts in information theory, signal processing, and statistics. They agreed on something important. Even if the pattern aligned loosely with prime multiples, natural systems can sometimes produce mathematical coincidences. Nature is not allergic to prime numbers. The pattern alone was not proof of intention. But combined with narrow band stability and Doppler compensation-like behavior, the anomaly gained weight. Privately, some researchers began using a quiet phrase, embedded carrier. The idea was simple. Imagine a carrier wave, a stable frequency acting like a base layer. On top of that carrier, subtle modulations could encode information. If the carrier were weak and masked within cosmic noise, only careful analysis would reveal the structure. To test this, they stripped away amplitude variations and focused purely on phase changes. Phase refers to the position of a wave within its cycle. Even if strength varies, phase relationships can hold hidden order. When phase data was mapped over time, small shifts appeared that aligned with the clustered pulse groups. It was as if the signal carried a secondary rhythm beneath the first. By now, the mood was no longer casual curiosity. It was disciplined uncertainty. By this were a beacon, it was not shouting coordinates. It was not broadcasting language. It was presenting something simpler. A repeating mathematical structure, resilient but subtle, persistent but not aggressive. And that raised a difficult question. Why subtle? If an advanced civilization wanted to announce its presence, why hide inside noise? Why not send a clear, powerful signal across wide frequencies? One answer is energy. Broadcasting across interstellar distances requires immense power. Embedding information within naturally existing radiation might require far less. It would be efficient, sustainable over long periods. Another answer is caution. A civilization might not wish to attract attention indiscriminately. A quiet beacon would reveal itself only to those who listen carefully enough to detect structure within chaos. But again, these are speculations layered on top of observations. The data itself remains modest. Weak pulses, narrow band, subtle clustering. As 3I Atlas moved farther away, signal strength continued to decline, but the core structure persisted just long enough to complete a full cycle of geometric alignments. Then gradually, it began to dissolve into background levels. The final confirmed detection occurred during a narrow observation window when atmospheric interference was unusually low. After that, nothing clearly structured could be extracted. The silence that followed felt heavier than the signal itself. Teams published cautious papers describing persistent narrowband modulation of unknown origin. They avoided dramatic headlines. They emphasized uncertainty, peer review demanded restraint, and restraint was given. Outside academic circles, rumors spread quickly. Online forums filled with bold claims. Some declared it proof of extraterrestrial intelligence, others dismissed it as statistical illusion. Most people moved on. But among those who had studied the data closely, something remained unresolved. Because the beacon theory is not really about aliens, it is about detection. It forces us to confront how we define noise, how much order must exist before we call something meaningful. How subtle can a message be before we miss it entirely? For decades, the search for intelligence beyond Earth has focused on strong signals. Clear broadcasts, repeating pulses like pulsars, but with unmistakable artificial patterns. We have built instruments designed to catch the loud and the obvious. What if the universe does not reward the obvious? What if intelligence, advanced enough, understands that the best hiding place is plain sight? As I speak to you now, with the patience that comes from many years of watching discoveries rise and fall, I am not here to claim certainty. I have seen anomalies collapse under scrutiny. I have seen mysteries solved in ways far less dramatic than imagined. But I have also seen how small irregularities can open doors to new understanding. The data from 3i Atlas will remain in archives. Future algorithms, perhaps more advanced than today's, may reanalyze it. Patterns that look weak now may appear stronger under different methods. Or they may vanish entirely. Science accepts both outcomes. The deeper impact may not be the signal itself, but the shift in perspective it inspires. Researchers are already discussing new search strategies. Instead of scanning only for loud transmissions, they are developing models to detect embedded structures within cosmic background radiation. Subtle modulations, low-energy carriers, mathematical fingerprints hidden inside natural processes. If nothing else, the anomaly has expanded our imagination. And perhaps that is the quiet power of this event. We expected fireworks. We found a whisper. We expected a declaration. We found a question. As 3i Atlas continues into the dark beyond our instrument's reach, it leaves behind uncertainty rather than answers, a thin thread of pattern woven into noise, now fading into memory. Maybe it was a rare natural process we do not yet understand. Maybe it was coincidence layered upon coincidence, or maybe, just maybe, it was something placed gently into the fabric of space, waiting for minds patient enough to notice. The universe is older than our species by billions of years. If intelligence has risen elsewhere, it has had time beyond our comprehension to think carefully about how to speak. So here we are, listening to the echo of a faint signal that may have meant nothing at all, or may have been the softest knock on the door of our awareness. And the final question is not whether 3i Atlas carried a beacon. It is whether we are ready to recognize one when it whispers instead of shouts.